Hello everyone. In this video I'm going to show you two guitars that I've designed and built. And the purpose of this is I want to show this relationship between pattern and geometry and beauty as it relates to designed objects. And the nice thing about the guitars I have is one is it's easier to understand than giant buildings. It can be used more arguably because it's a smaller object, and I can hold it in my hand, I can show you the object, I can show you the drawings, and we can go through these things. So I will show you some drawings as I usually do, but before I do that, I want to show the guitars here as well. So here I got one of these is the acoustic guitar here, and we'll be looking at the drawings of it. You can see it's a pretty big guitar, but the shape of it helps make it look dynamic. Both the guitars have a similar idea that I'll talk about in drawing. They're meant to sort of look dynamic, but be simpler to play. And I'll talk about that in drawing. So here you go. Here it is here. I want to point out also, sort of as an aside, I made this out of reclaimed myrtle wood. You can see the back there. The grain pattern is really quite striking, which is just a natural pattern that is really quite beautiful, besides the man-made pattern of the shape of the guitar that I'll really be talking about. They can play off of each other like that. Super interesting. And then I have an electric guitar as well, which is right here. You can see again, they're meant to sort of play off of each other, so they got the same sort of oval bottom, the bottom of the bow down here, but this is an electric guitar version. The cutouts can be different, the sizing and all that stuff can be different too, and sort of invented this tweed pick guard on this one, tweed for my last name. So there's this one a little more dynamic, but again, meant to be sort of, both guitars are meant to sort of be very functional in playing, but also sort of have a dynamic, like they're dancing themselves. So let's look at the drawings, and I can explain how I actually created these and how I use patterns and geometry to really help along the way.
So here's a drawing I made some time ago of the acoustic guitar to help explain how I designed it. And I did make and design this guitar many, many years ago. And at the time, I was sort of really beginning this investigation of patterns and geometry and how they relate to beauty and design. And so early on, like many people, I was really sort of obsessed with the golden section. I'll talk a little bit about that later. I'm not entirely that way today, but then I was. And so what I started the design process was over here in this drawing labeled 1. And we see here I've got a rectangle here. That's a golden section rectangle, meaning the length of its side to each side is in a proportion of 1.168, and I basically just doubled that up. So I have two golden sections sitting on top of each other, which ultimately the entire body, which is the primary visual element of the guitar, would fit within. And then on top of that, I got this right triangle, right meaning there's 90 degrees there, and purposely the halfway point of the bottom line of this triangle hits the halfway point of that rectangle very specifically, and then the sides come up. And I don't remember now, quite honestly, but I think like the lengths of the sides somehow related to each other in golden section as well. And the goal was to sort of use these bounds as a framework geometry to build within. And that's when sometimes I talk about how you can use these patterns not just strictly on the surface of the elements, which I will, as we can see in the upcoming diagrams here, but also in the grid and the framework. The reason why I don't like to use the word grid is because this really isn't a grid. It's more of a framework. It's a set of geometries that contain the whole design and keep it consistent and sort of visually coherent with one another. So the whole guitar fit in there and strategically hit specific points. Now, each particular element or each curve of the guitar, as we'll see here in 2, is either made of a perfect circle or this particular shape of an oval. That's the main bow of the guitar right here. And each of these elements, each of these sizes of these circles and ovals relate to each other in scale based on the golden section as well. So there's the biggest circle, which contains the big oval. I've scaled down this shape, but it's meant to correspond to these shapes over here. So this big oval is really the same as this one, just in diagrammatic form. And then each of the various other circles are all smaller based on the golden section. And those are the circles that are used, and you can see here, and this is literally how I drew it in AutoCAD. I would draw those circles to where I needed to go, and then I'd either touch important tangent points of the circles, or the circle would tangentially touch the triangle, or the outside rectangle, or whatever the case might be, to line up to make this so it's all within the golden section. You can see, of course, there's some important points, like the bottom of the guitar touches exactly the point where the triangle, the starting triangle, and the rectangle touch, right? They also touch the top of the guitar, so they're in bounds. And it's also the sides of it. So if you were to draw a rectangle around the uppermost, sidemost, and bottommost parts of the guitar, they define the edge of the rectangle. Similarly, sort of this line comes up. It's the edge, the widest part of the bow tangentially to this angle, and the widest part of this top part all come up and form the headstock right along that line to really visually reinforce that line. So you can see ultimately it comes together as I sort of fade back the geometry and fade up sort of the guitar and the wood texture itself. You can see how the guitar sort of all falls out of those very specific geometries. Now you could argue that to a certain degree this guitar is asymmetrical. Now there's, in some cases it is more so than others. Like the cutaway for the fingering is obviously different than the other side where you don't need the cutaway. But more specifically, the thing that makes this dynamic is that this oval is rotated about the primary axis of the guitar, right? And so that makes this side a little bit different than this side. But I hesitate to call the guitar completely asymmetrical because that oval is symmetrical. It's just the axis of symmetry of that oval is not the same axis of symmetry as is in the rest of the guitar, right? So, or what is traditionally the axis of symmetry for a guitar. And that's what makes it fun, right? So it's playing off these ideas of symmetry. So obviously there's mirror symmetry. I'm playing off the concept of mirror symmetry by understanding that there's two different axes. And note that this axis here, this is, you can see I posted here of this bottom bow, it's parallel to this overriding geometry on purpose, right? So I understand I have these different axes in here, and I'm use certain things symmetrical to that axis and certain things symmetrical to the primary musical axis of the neck of the guitar. And that sort of those contradictions make it dynamic. Similarly, scale symmetry, I'm using, whenever you're using the golden section and scaling things down or up by a certain proportion, you're using scale symmetry as well. So I'm using all those different kinds of symmetries I've talked about in other videos to sort of compose this guitar. And it's fun and it's great. And the great thing about this, the way that the bottom sort of does rotate up and in, I can get a really big bass to get a full rich sound, but still make it easy to reach around and play. Because it's not sort of getting in the way, so it works really well. It's a nice little guitar to do. So if I come to AutoCAD, well, I was gonna jump in here. Here's the AutoCAD version of the sort of lines that I used to cut it out. But I just want to show that the reality is what I had shown in that sketch is literally what I have here. So you can see those basic shapes. I had this all the way through the entire time. That's where I started with the green lines, spacing the geometry, and all the moving the blue lines and scaling them around to sort of solve that problem. And if I pan out, you can actually see how many iterations I do to get there. It takes a lot of work. It always takes a lot of work to iterate any design. But when you're trying to adhere to such rigid geometric rules, at least for me, I'm no expert in it, I would say, because generally design isn't taught so specifically this way anymore. So I sort of was figuring it out the way I go. But nonetheless, even if I was more skilled, it certainly takes a lot longer to do than not. And if you watched my video about how I organize my CAD files, you'll note I started up here in concept and I work down and over, and I can trace my thought pattern all the way to that final design. But even so, if I come up all the way over here, you can see even in the early stages, that core geometric framework is there all the way from the beginning, right? And so then years later, it's been a couple years now since I designed and built it, but it was several years after I made, many years, I should say, after I made the acoustic, I made the electric one that we saw at the beginning of the video. And here it is in its CAD version. The one thing I wanted to keep the same was I wanted to use a basic oval pattern down here and sort of play off that same concept that some of the guitar in the neck, in particular, where the music is made, is sort of by nature vertical axis. But then if I rotate some of the geometries of thinking about that oval down here, I can get that same dynamic look. I can sort of shift the geometries there as well. The difference is I've sort of, in my opinion, I've grown away from the golden section to be so specific. My thoughts are, if you're using a consistent proportional system, you're going to be good. Does it have to be exactly the golden section? I don't think so. Maybe there are some studies that say it's the best one. Okay, maybe it is better than, I use some 2 to 3 rate 1 to 2 and 2 to 3 ratios in this I'm going to show in a second. Maybe they're slightly better than those. I think the human mind can't quite do those calculations. I think any sort of consistent mathematical proportional and scaling system you use is far better than just using a random system and not using any and sort of being very inconsistent in it. So I think it's as equal, any proportional system, 1 to 1, 2 to 1, any number that you could generally sort of come up with is good. So anyway, if I turn on again, what I did is what I started in here is yeah, here we go. Here's the grid. I started with a grid, and it's a little hard to read. I was experimenting, and I can't say that it fully worked. I started with a one relationship of 1 to 2 and a relationship of 1 to 3 grid, and I said, what would happen if I actually used both of those grids simultaneously? That'd be a fun experiment. And so that's how I designed this. And you can see that the yellow is actually a 1 to 3 grid based off of a base rectangle, and the red is a 1 to 2 grid based off of the base rectangle. And of course, at certain intervals, they add up to each other. And then to do some of the design work of the headstock, I had to actually extend the grid in several directions just to get certain center points for circles and things of that nature. And so that is the grid. And again, you can see same thing, like to work on such a complex grid and trying to get everything to work together. And a guitar is complicated itself. There's lots of requirements to make the notes come out right. It took a lot of iteration, but you can see the very first thing I did, other than I started sketching in my sketchbook, and then I translated that sketch into a quick CAD element here. But you can see once I did that, the first thing I did was define grids, and it took me even a couple times to get the sizing of the grid correct, even though they all based off the same 1 to 2 and 1 to 3 grid ratios, but they have to match certain sizes to make the guitar work and work together as a unit. And so it took a few times to get together, but as soon as the grid worked out, it's there every time. You can start to see right here, this literally is that same oval that I started from the other guitar, and I put it into place. And I changed lots of things from that point forward, obviously, to get to the final guitar. I wanted to make it a little bit different. I want to make it similar, not identical to the previous guitar. So it's almost like a brother or sister to that other guitar, and I think it came out well. And again, this is a fun guitar to play, and all based on geometry. So I do find that doing such extensive geometric research or geometric application on buildings becomes tough. There's more functional requirements. They're just more complex entities. But even at a basic level, even things like the basic, like fit it into a triangle and rectangle, I think can be quite strong. And sort of relating it, if the one building example that I did show of the house that was based off the Pentagon sort of starts to get there. But I think this is a more clear example that's more directly applied. So I hope you enjoyed this video, and I hope it helps you make great designs and great drawings.